So I'm Jennifer Mercer. I'm in my day job a program manager with NSF's Arctic Research Support and Logistics and also Arctic Sciences. And I am one of the co-leads for the atmospheric collaboration team within IARPIC. Sarah, for some reason the IARPICcollaborations.org isn't loading when I go to the website. It may just be me. I can get to the agenda page just fine, but then I can't get to the other pages. And I don't know if it's my computer or if there's something going on. But anyway, for those who aren't familiar, I'll just talk for a couple of minutes. So IARPIC is the Interagency Arctic Research Policy Committee. It's a small organization within the Executive Office of the President designed to coordinate US federal agency efforts under the Arctic Research and Policy Act. And we currently are operating under the Arctic Research Plan it's a 5-year plan. It's renewed updated every 5 years for the plan that spans fiscal years 2017 through 2021. And there are 4 policy drivers within the plan. So those are related to Earth systems, Arctic resident health and well-being, environmental stewardship, and national security. We have 9 collaboration teams then that cover a range of topical interests. And IARPIC collaborations, you can go to the IARPICcollaborations.org webpage, which anyone can join. We often are giving plugs for that and encouraging members to participate and post on there. But that brings together the participating US federal agencies with all of the university, industry, and international partners to help accelerate progress toward the research objectives in the plan. Each of the collaboration teams aims to hold monthly meetings focused on a theme that relates to one or more of their research objectives. And so this meeting here, our theme is basically that satellite platforms provide unique and important observations to help understand processes governing Arctic climate. So we are hoping to learn about current and upcoming satellite missions that help provide spatial context on the key drivers and responses of the Arctic energy budgets. We do have performance elements, which I don't know if, so you are accessing it there because you can see it on the screen. So we have performance elements that relate to this theme, which you can go and check those out. I won't read those to you, but they are performance elements 2.1.2, 2.2.3, and 2.3.1. Sarah's guiding you towards those right now. And so, let's go back here. So, yeah, so we have 2 speakers today. And I believe that, and Tristan, I don't know how to pronounce your last name, but I believe you're the first speaker. But I think we'll do roll call and stuff first. Sarah, is there anything else?
No, that was a great overview. Thanks for doing that, Jen. Does anybody have any questions about IARPIC before we get started? Great, then we'll just do roll call. And the way that we like to do roll call, and we like our meetings to be as open and accessible to anybody, and urge you to speak up and ask questions and feel free to contribute. During roll call, if you have something that you want to mention about your institution or an upcoming event or a new publication, please share that in the roll call. The way we'll do this, because we have a manageable group today, is we're going to do it by region. So if you're in the state of Alaska, can you introduce yourself? Don't forget to unmute. Seiji, I think you're in Alaska, aren't you?
Me? No, I'm not in Alaska. I'm in
I thought you were. Sorry.
Virginia.
Ah, okay. I thought you were at UAF. Now I remember you're NASA. So nobody from the state of Alaska. Okay, anybody on Pacific time? Nobody on Pacific time? Okay, then let's try Mountain. Oh, come on, is everybody?
We're all Eastern time?
Is everybody Eastern? Okay, let's.
Oh, sorry, Sarah, Sandy's here.
Sandy, thank you. Wait, you're the only one, the outlier. Okay. Thanks, Sandy. And Sandy, you want to introduce yourself and your organization?
Yes, sorry, I'm joining a little bit late here. My name is Sandy Starkweather. I'm the Executive Director of the U.S. Arctic Observing Network, and I'm a research scientist at NOAA's Cooperative Institute with the University of Colorado.
Great. Anybody else in Mountain Time? Okay, then Central Time. We usually don't have anybody Central Time.
I am Central Time. I'm in Wisconsin.
Okay, who's this?
This is Tristan.
Oh, okay.
So I am just, I guess, to introduce myself, I'm at the University of Wisconsin. Also the director of the Cooperative Institute here in Madison. So there's a nice connection there. And I primarily work on satellite observations. I've done a lot of global research, but my research is drifting more into seeing what satellites can tell us about the Arctic region and how they can supplement ground-based observations that are obviously difficult to make in that area.
Great. And Tristan, how do you pronounce your last name?
Oh, sorry, it's Lequier.
Oh,
Lequier.
okay.
Thank you.
Thank you. Okay, let's go to the East Coast, and I'll just start at the top. And Seiji, you want to go first?
Yeah, my name is Seiji Kato, and I'm at the NASA Langley Research Center, and I'm involved in the series project, which is responsible for providing the top of the atmosphere and surface radiation flux products using the satellite observations. And I'll explain a little bit more in detail during my presentation. Thank you.
Thanks. Okay, who's next?
I'll go. This is Barry Leffer. I'm at NASA headquarters in the Earth Science Division, and I'm the program scientist for the Tropospheric Composition Program. And excited to see our talks today.
And Barry's also a co-lead with me for this group.
Okay, Lynette, you want to share with us your information?
Yeah, sure. So I'm Lynette Boisvert, and I am a sea ice atmospheric interaction scientist at NASA Goddard Space Flight Center. So I'm interested in how the changing sea ice pack is affecting like the local atmosphere, like evaporation and things like that. And I'm also the deputy project scientist for NASA's Operation Ice Bridge as well. So, yep.
Thanks, Lynette.
Great.
And Lauren?
Sure. I'm Lauren Zamora. I'm at the University of Maryland, and I'm a contractor at Goddard Space Flight Center. And I use satellites and models mostly to look at aerosol cloud interactions.
Thanks, Lauren. And then we have RDCRLREA. I'm not.
Yeah, sorry, that's an ID. It's not my actual name. So my name is Ross Alter. I'm a research meteorologist at the Cold Regions Research and Engineering Lab in Hanover, New Hampshire. And this is my first IARPIC meeting and my first one specifically with the atmosphere group. And my background is mainly in land-atmosphere interactions, but this is really just my first step into the Arctic domain. So I'm here to learn and contribute in any way that I can.
Glad to have you. And is it Ross or Russ?
It's Ross, R-O-S-S.
Okay, thank you very much.
Welcome, Ross.
Sure.
Glad to have
Thank you.
Christine.
Hello, this is Christine Mattia. I work at NASA headquarters, and I help coordinate our participation and involvement in IARPIC.
And B.H. Khan. Christine, is that Dr. Khan? Do you know?
No, it's a different Khan. So I know Ralph Kahn's out in Boise, Idaho on the FIRE project right now.
Okay. All right. Well, maybe I'll just we'll go on to the next one, which is the mysterious S.
Hi, Sarah. Yeah, this is me. I'm Stephen Peckham. I'm also a newbie here at the Cold Regions Lab in Hanover. Ross has already introduced himself, and I too am in the same lab, just a little different part of the building where our offices are. The previous person had mentioned Ceres out in Boulder. I was there with NOAA for 15 years. I did a lot of weather research, forecast model development. About 4 years ago, I came here to the Cold Regions Lab, and I'm trying to move away from just doing WRF and exploring surface energy balance. I heard sea ice. There's some people here I work with that also are looking at sea ice. So I'm very interested in this presentation in this area of surface energy balance and different areas we could apply it. So great title. It obviously brought a couple people in who are new.
Great, we're great to have Krell on board. I can tell Martin's been doing good work there. So thank you very much.
That's right. He has gone forth and preached the word.
We can tell.
Thank you very much. And Jeff Key, I see you've joined as well.
Hi, yeah, I'm Jeff Key with NOAA NESDIS, the satellite part of NOAA here in, well, we're located at the Cooperative Institute for Meteorological Satellite Studies that Tristan is the director, now the new director of, fairly new. Anyway, I do satellite remote sensing of the polar regions, including surface radiation budgets, so I just called in to learn something.
Great, glad to have you. So did I miss anybody? Is there anybody else who didn't get a chance to introduce themselves? All right.
If not, Sarah, I'll just, I don't think I said at the beginning, so there are actually 3 co-leads, and Barry and I are both here on the phone with everyone. Our third co-lead, Heist de Boer, is not able to be with us today, but all 3 of us are very active in managing this group, so you can always reach out to us. And for any of the people who are new to this meeting and the Atmosphere group, we do encourage you to make sure that you join the IARPIC collaborations portal, where you can see a lot of announcements and other upcoming meetings and stuff. So.
And for those who don't know, HICE is in Ceres in Boulder, Colorado, sort of 1 foot at NOAA and 1 foot at the University of Colorado.
Thanks, Barry.
Great. Well, I am going to stop sharing my screen, and because I think we're ready to tee up the presentations, right?
Yeah, unless there are any member updates or announcements. Nobody made any during roll call, which they're welcome to do, but if anybody has any agency updates or announcements, maybe go ahead and make those. We sort of flip the agenda around here, so it's not exactly what you saw on the screen, so that we have time after the presentations to have discussion, and we find that to be really effective. Oftentimes, it's bringing together presenters who haven't necessarily conversed in the past or aren't really up to speed on what each other are doing, and then other members as well. So we tend to have lively questions and discussions amongst the presenters and all of the attendees in the group. So we like to leave time for that, for open discussion. So if anyone has any other announcements and stuff, we could take those now, and then we can go into the main part of the program, I think. Okay, so I understood correctly, Tristan's going to speak first, is that correct?
No, I think Seiji is going to go first.
Seiji's going to go first. Sorry, I mixed it up again. Okay. So Seiji, you uploaded your presentation. Are you able to share your screen? Or Sarah, did you guys work that out?
We did. Okay. I think I can share. Where's my share screen?
Yes, that's right. Scroll over the bottom.
And share.
Yep, it's coming up. And now just make it presentation mode.
Isn't it this?
It's perfect. Looks perfect. Okay. And we can hear you perfectly, so thank you.
All right. So I'm going to talk about the Arctic energy budget, but primarily focusing on the radiation budget at the surface. And I'm going to present what satellite observation can do today and what the issues are right now. And for from the energy budget perspective, the goal of satellite observations are, in my view, the three overarching goals. One is deriving and quantify climatological mean energy budget and its variability and changes, and quantifying radiative forcing. And the second one, the third one is understand the key processes contributing to energy budget change. And today I'm focusing on that status of achieving first goal, the deriving and quantifying climatological mean energy budget, its variability and changes. And I can't move to somehow it's stuck.
So it should just advance the same way.
Yeah, it did, but it's not sure why. But stop sharing now, or?
No, no. We can see the presentation. We can see your second slide.
I want to go next slide.
You might need to make sure that you click on the Zoom screen in order to be able to forward.
Oh, Zoom screen.
Yeah, except he was forwarding just fine the first slide.
Oh, yeah, okay.
Here you go. You got it.
Okay.
Thank you. Thanks,
All
Sandy.
right, so I'm sorry. Outline of this talk is just current status, and I'm start with the method, briefly, method to deriving top of the atmosphere and surface radiation budget, and present the radiation budget with the high confidence. What's the radiation budget we can provide with a high confidence? And then lastly, challenges in driving polar radiation budget. And I provide one just simple case that illustrates the problem in deriving the surface radiation budget. And in a series project, top of the atmosphere radiation flux is derived from almost directly from observation. And the series instrument measure the broadband, shortwave, and longwave radiances, and from currently on 4 satellite platforms, and Terran, Aqua, and Sumi NPP, and NOAA 20. And the broadband radiances are converted to broadband irradiances, fluxes, using a very a little bit complicated empirical model. And that conversion factor depends on we call scene type, the surface type, sea ice, land, open water, and also cloud fraction, cloud optical depth, cloud face, and so on and so forth. And that's why we need an imager co-locating with the series instrument, and that's such as MODIS and BEERS to identify the scene types over series footprint. Like top of the atmosphere irradiance, surface irradiance are derived rather indirectly. And surface irradiance are derived by running radiative transfer model. Inputs for that model is our snow and sea ice map. That's a daily map. And the cloud and aerosol properties derived from the imager, MODIS or BEERS. And the temperature humidity profile we take from reanalysis. And among those cloud properties, cloud fraction and optical thickness and the cloud base and top heights are key cloud properties influencing surface observations. And then since the top of the atmosphere irradiance is directly derived from observation, we can use that observation to constrain the surface radiation. And at the surface, spectral surface albedo and emissivity are needed as a lower boundary condition. And Tristan will talk a little bit about the spectral emissivity. And and because many inputs are used in a radiate transfer model to compute the surface irradiance, the surface irradiance are more susceptible to the error in inputs and have the larger uncertainty than TOA irradiance. And the uncertainty in the flux irradiance averaged over larger area and a longer time period is small, and uncertainty increases as the size of the area and the time of period decreases. So the smallest uncertainty over Arctic comes with this, the irradiance, surface irradiance averaged over entire Arctic and for the climatological sense. So this is the 10 years mean of net shortwave irradiance at the surface and a net long wave irradiance at the surface, and a net shortwave plus long wave irradiance at the surface. And net shortwave irradiance is primarily a function of insolation, and net long wave irradiance is mostly negative, although the value of net long wave irradiance is the absolute value is smaller, much smaller than the variability of shortwave net shortwave irradiance. And long wave net is more negative during the summertime and less negative during the winter. And when we add together, net shortwave plus long wave is primarily the function of insolation. So net radiation is primarily driven by the shortwave radiation. The seasonal variation is driven by the shortwave radiation. And the bottom plots are for cloud radiative effect, defined by all sky irradiance minus clear sky irradiance. And again, shortwave cloud impact to the shortwave is negative and large during the summertime, and small in the, during the winter time because of the insolation. And the long wave effect is positive, so the clouds are warming the surface by long wave. But when you get put together for a total cloud effect, the cloud effect in winter time is positive, and during the summertime is negative. But the shape of seasonal variability is primarily driven by the shortwave irradiance. So this, we can provide this as a certain high confidence. The reason we believe that the small uncertainty with a larger area and a longer time period is following. We use the surface observation to evaluate our computed surface irradiance. And we have 4 validation sites in the Arctic. It's not enough, but these are the 4 provide the surface observation, the accurate surface observation for a long time. And when we combine the 4 sites and compute the monthly mean at each site, and take a difference between a computed surface flux and observe the surface flux, and plot the monthly mean difference histogram, we see that the mean bias combined over 4 sites are very small. And on the left side is a shortwave bias. On the right side is long wave bias. The mean bias combined over 4 sites are this edition 4.1 is 3 watts per square meter for shortwave, and long wave is about -2 watts per square meter. So this indicates that the 4 sites does not cover the a very diverse range of the surface type in the Arctic, but we think that when the flux is averaged over large area, we have a very small uncertainty. Another indication that we have a smaller uncertainty in the flux average larger area is this showing here. This is the zonal cloud fraction comparison. The red line is the day-night cloud fraction derived from MODIS, and the blue line is the day-night cloud fraction derived from Calypso CloudSat. And this is the 3-month average, but this also indicates the cloud fraction difference between passive sensor, which is MODIS, and the Calypso CloudSat, which is active sensor. We believe that a more accurate the way to derive the cloud fraction agree fairly well if we take a zonal mean and a 3-month average. So here's a kind of a summary so far. What we can provide is the we can do with the satellite today is a quantified annual, seasonal, and monthly mean radiation budget over polar region or Arctic region with uncertainty, and quantifying the spatial and temporal variability of annual, seasonal, monthly anomalies of radiation budget over polar region. I'll get a little bit here, second bullet and next slide. But the larger uncertainty is associated with radiation budget with a smaller area, and uncertainty increases as the size of area decreases, and also large uncertainty in detecting the trend in polar radiation budget. And here's the example showing the variability of Arctic radiation budget. And the top plot is the showing with the blue line is the anomaly time series of downward long wave irradiance averaged over the entire Arctic at 60° and 90° north. And that we can provide how we can quantify how variable that this long wave radiation by computing the standard deviation of these anomalies. And the standard deviation of 60 to 90 north, these anomalies are 3.1 watts per square meter. And if we take the tropics from 0 to 8°, which has about the same area of 60 north to 90 north, and the variability of downward long wave radiation over this tropical area is about 2.1%. And so we can say that with some confidence that the variability of long wave downward radiation over Arctic is larger than the variability over tropics. And but same thing, we can do the same thing for outgoing long wave radiation. And this blue line is the outgoing long wave radiation averaged over 60° to 90°, the anomaly of those. And that is 1.7 watts per square meter. In contrast, anomaly of OLR over tropics from 0 to 8° is 2.4 watts per square meter. And this large variability in the tropics is primarily due to the ENSO, El Nino and La Nino. And just to note, the time to detect the trend increase is proportional to 2/3 power of the standard deviation, these values. So if signal is the same, it's for downward long wave radiation at the Arctic, it takes longer to detect the trend. And the issue now I'm moving on to issue. And I provide a simple example. This is the simplest example associated with the temperature inversion. And the Arctic, if you measure the temperature, vertical temperature profile during the winter time, Arctic has a large temperature inversion. The surface temperature is much colder than the air temperature, and sometimes the delta T, the inversion strength is greater than 10 or even reach to 20 degree K. And so if we plot the downward long wave and upward long wave observation by this blue line, this is the time series of long wave radiation observed at, this is Antarctica on the Showa site, but in the polar region, and with the blue line. And the green line is our computed value. And this day, second day of the month, the downward long wave radiation is very small, indicating the sky is clear. And but our upward long wave radiation, the skin temperature is warmer than the actual skin temperature. So our cloud retrieval fooled because the actual surface temperature is a clear surface temperature is the warm colder than the skin temperature we have as initial condition. And so we put the clouds, retrieve the clouds, and so our downward long wave radiation is much higher than the actual downward long wave radiation. This difference is much larger than the simple temperature error in the computation because of its cloud retrieval is fooled by the colder surface temperature. This illustrates the some difficulty to number one is computing the Arctic radiation budget at a smaller scale, and because of it's not just simple direct impact from temperature to the computation. It's going through the cloud retrieval, and the error might be amplified because of the wrong clouds. So the larger uncertainties in quantifying regional surface budget, radiation budget, and we don't have enough surface validation sites, but a field campaign such as NICE or future field campaign like a Mosaic will help to improve our estimate. And active sensors, the Calypso CloudSat, have been helpful, but new instrument that Tristan will present, focusing on polar region, will help to improve the radiation budget estimate. And the quantifying polar radiation budget change with time, with a trend, is challenging. And we don't have enough data to estimate uncertainty in the trend over polar region. And lastly, I put the summary slide, and I said all in my presentation. So I just leave summary slide here. Thank you very much. Okay.
I think we're just reading here.
Oh, okay. Oh, so I just leave it
give everyone
like that?
a second to read the summary slide.
Leave like that?
Yeah, and if anyone has any questions, feel free to go ahead and ask. So I'll ask a question, and I think it goes back to, you were talking about how some of these upcoming campaigns will help. Are there new instruments on the horizon, or besides just campaigns, is it really just is the answer just more measurements, so greater coverage in measurements to help?
Yeah, I think the new instrument too, that I think Tristan will introduce the instrument measuring the far IR radiation. Mm-hmm. But because of the over Arctic, the surface type is so diverse, mm-hmm. even spatially and temporally, like freeze and the melts of sea ice, has a large variation in the surface albedo, and that's land and ocean, open water, and sea ice. We need this is very unique to the Arctic, and in the sense that the 4 validation sites is not enough to understand that the error in a smaller scale. So yes, new instrument, and also needs a new sites or more field campaign to provide energy budget data.
Okay. I'll save further questions for the discussion. Does anyone else have questions for Seiji, or we can go on to Tristan and have more discussion after that? Okay, thank you, Seiji.
All right.
Stay on the line though, because
yes,
for the discussion.
So Seiji,
I have to stop sharing.
Yep,
yeah,
you did
okay.
perfectly. Okay, and Tristan, you can share now by scrolling along the bottom to the share button. Perfect.
Okay, did that work?
Yeah, it did perfectly. Thanks.
All right, excellent. Okay, so yeah, I think I suggested that we present in this order. I think that worked pretty well, because I think Seiji set the stage nicely for what I'm going to talk about, which is a new instrument, a new satellite mission actually, really dedicated to trying to solve or improve our understanding of the Arctic energy balance. It's actually both poles that we're interested in looking at because it is a satellite mission. But most of the material I'll present today, and most of the motivation for this, of course, is the Arctic, because it's changing so quickly here. And so I want to start with just sort of a basic diagram here and point out a couple of, I guess, key elements of the Arctic energy balance here. So this is kind of a traditional diagram of the energy balance. Most of the time this is shown as a global diagram, where you have at the top of the atmosphere the thermal emission going out from the planet and the amount of sunlight coming in. And then you have these various energy flows indicated by these arrows in the diagram, which represent the exchanges of energy between the surface, the atmosphere, and space. And I really just want to make 2 points here. So these are the numbers. I would call these basically the state of the art. They come from a program called the NASA Energy and Water Cycle Study, of which Seiji was a part as well a while ago, and I was for several years. But the idea here is that I just want to raise a couple points. One, that based on these numbers, there's a pretty enormous deficit, as we all know, of energy in the Arctic relative to other latitudes on the planet, and that requires this fairly enormous number, 1.2 petawatts of energy, to be transported into the Arctic from lower latitudes on an annual average. I'm bringing that up right now because I'm going to talk about in a minute some implications of the Arctic energy balance for other areas of the Earth, for climate on the other areas of the Earth. And that really stems from the fact that this 1.2 petawatt deficit of energy is what I call kind of the Earth's thermostat. It's basically the way the Earth cools off and releases some of the energy that's absorbed down in the equatorial regions. The other thing I want to point out is if you look at the various numbers on this diagram, the various energy flows, one of the things you see is that the long wave, or the thermal components, tend to be fairly significantly larger than the visible components, the solar components on this diagram. Now, that's not to say that the solar is not important. Seiji showed that the solar has a huge annual cycle, and of course, going from sea ice to an open ocean surface has an enormous impact on the albedo and changes the amount of absorbed solar radiation. But I do want to make a point, because it's going to lead into what I'm going to talk about with the PREFIRE mission, that these thermal fluxes, the amount of energy emitted from the surface and the amount of energy trapped by the atmosphere, the atmospheric greenhouse effect, are also significant players in this Arctic energy balance. And they, if you look at these error bars, these plus or minus numbers on here, I'm referring now to the stuff in the pink circle. The error bars are still relatively large on some of these numbers. And in fact, speaking to that a little more, if you pull together other sources of this information, this is a busy diagram, one that we're working on publishing now. This actually combines not only the observational estimates I just showed, but all of the best estimates from the modern reanalyses that we have, and also climate model estimates. What you can see is it's not just the observations that have large uncertainties, but there's a large spread in reanalyses and also a large spread in climate models for these thermal fluxes. So this is a significant source of uncertainty that has some fairly significant implications for the Arctic climate. And so I'm going to show a couple of examples of that before I get into this new observing system that we're hoping will help reduce some of this uncertainty. Coming back to the main point that I mentioned on that first energy budget side, when you actually then take all of the component fluxes in these models and observations and actually compute over the course of the annual cycle, and this kind of again follows on some of the results that Seiji showed, but now I'm just showing the net energy transported into the Arctic region from the lower latitudes. So this is what's known as the surface energy imbalance. It's the deficit or surplus of energy that you have at the surface. And again, any kind of surplus or deficit of energy has to somehow be balanced by energy being transported in from elsewhere. And what you can see is if you look at, for example, the purple bar here, this big purple swath on this diagram, that shows the range of values that are estimated by current climate models. And what you can see, I'm kind of pointing out, if you can see my cursor, or if not, the yellow bar here, that indicates in the summer months, there's about a factor of 3 spread in the Arctic surface energy imbalance predicted by our current climate models, the CMIP5 models. The observational spread is shown here in blue. It's a little bit less, but you can still see there's a large uncertainty in the observations as well. And what I'm showing here on the left side is just sort of a schematic, again, kind of making this point that it's this Arctic energy imbalance that drives the general circulation of the planet. It drives 2 different main circulation patterns that we have on the planet. The Hadley circulation, which transports energy from the equatorial regions to about 30 or 35 degrees north. And then the extratropical circulations, which are more sort of a horizontal. There are extratropical storms, our cyclones that we get that drive our weather at mid-latitudes, that mix cold air from the Arctic down to lower latitudes and warm air from the lower latitudes up into the Arctic between about 35 and 60 degrees north. So this uncertainty on the right-hand side of this diagram directly leads to uncertainty in our ability to predict the weather on other areas of the planet. And as a specific example of that, so that was just a cartoon schematic, but to show that this is indeed the case, here is just one set of results where a colleague of mine introduced some uncertainty in one particular parameter in the CESM climate model. Here, this was Zhenglei Huang's work, where he changed the surface emissivity to be more representative of what laboratory experiments show that it should be, relative to some fixed values, which is what current climate models used. And he just reran today's climate, a simulation of today's climate using in this case, the CAM5 model. So this is CESM1, if you're familiar with that community or system model. And what we're showing here is the departure from the base state of CAM5 when you make this change to a more realistic emissivity model. For things like temperature on the left here, you can see some areas the temperatures change by up to 2 to 3 degrees just by simply changing the surface emissivity, which governs how much energy gets emitted from the surface into the atmosphere. If you look at sea ice fraction, you can see again in some areas, some of the same areas, you have changes of 15 to 20% in sea ice fraction. And not only that, you can actually see that some areas experience increases in sea ice while other areas experience decreases in sea ice. So that kind of shows that the weather patterns or the circulation patterns in the Arctic are actually affected by this change in surface emissivity. And in the upper panel here, I even have snowfall. So a quantity that may or may not, you may not even think is necessarily related to the surface energy flux into the atmosphere, but through a variety of feedback processes and changes in the general circulation, we see changes in snowfall distribution as well, fairly significant 30 or 40% changes in certain regions of the Arctic. Going down to some smaller scale, and this will be sort of the last result I'll show here as an example of the impact of this errors in the surface energy balance. We can actually look at things like the surface ice sheet processes. And so what we did here was we took a fairly sophisticated model of ice sheet dynamics, which uses as input radiation, temperature, and snowfall, and then simulates things like the refreeze process, the melting process, and the accumulation processes, and then also the flow of the ice sheet. And what we did was we ran a perturbation in this model of just 10 watts per square meter, which is actually fairly significantly smaller than the uncertainties I was showing you in the greenhouse effect and the emissivity on the previous slides. But just to see what an impact of 10 watts per square meter would have on various processes or various properties of the ice sheet. And so what I'm showing here is for 3 different locations on the Greenland ice sheet, the temperature change relative to a control simulation when you add an extra 10 watts per square meter of energy into the surface. And you can see that the temperature can change by up to 2 to 3 degrees in certain areas with this kind of 10 watt per square meter radiation bias. Surface mass, interestingly, so this is the effects of runoff and evaporation. Surface mass balance can change by 10 to 15% with just a 10 watt per square meter bias in radiation at the surface. And when you go down to the process level and look at individual things like melting rates and refreezing rates, you see that this change in surface radiation has significant impacts on all of the individual processes as well. This is kind of a summary slide just to show sort of the net effect on one quantity that we're very interested in, which is the surface mass balance of the ice sheet. That, of course, is the direct driver of sea level rise on the planet. And what we're showing here is now a variety of different perturbations from adding 20 watts to reducing by 20 watts the amount of radiation going into the surface. And if you just focus on the dark blue here, you can see that by over this range of about plus or minus 20 watts per square meter, which again is not inconsistent with the uncertainties that we right now have in our understanding of the surface energy balance, we can get about a change of 14 gigatons per year of runoff off the ice sheet. That's a tremendous amount of water that is right now kind of our error bar due to these surface energy imbalance errors. Okay, so moving on, just to wrap up here, the PREFIRE mission is kind of dedicated to trying to improve, like I said, our understanding of the greenhouse effect and surface emission. This slide just shows one of the kind of striking motivations for running this PREFIRE mission. And basically, I argue that a lot of the uncertainty that we currently have stems from the fact that we've never measured radiation systematically at wavelengths longer than about 15 microns with current sensors. Series that Seiji talked about before is the one exception, but Series only makes one broadband measurement from 4 microns to about 100 microns, and it doesn't provide the spectral variation that you need to separate things like the surface emissivity from the atmospheric greenhouse effect. All of our other sensors that can do that have a wavelength cutoff at 15 microns, yet if you look at the Planck function for things like the outgoing long-wave radiation in the Arctic or the downwelling long-wave radiation, which represents kind of the atmospheric greenhouse effect, you see that almost 60% of those energy fluxes actually lies at wavelengths that we've never measured longer than 15 microns. I'll skip this slide for time, time. So what PREFIRE is actually going to do is document for the first time the spectral fluxes from 5 all the way out to at least 45 microns. We think we actually will be able to get out to 54 microns, which will now cover 97% of the outgoing long-wave radiation, and even a little more than that of the downwelling long-wave radiation into the surface in the Arctic. So we're going to make this measurement for the first time, and I refer to that in my title as kind of opening up this new window, this far infrared window into the Arctic climate processes by documenting these far infrared spectra. The way we're going to do it, and maybe I'll just go on to the next slide here, this is kind of our mission concept. We're going to use 2 different CubeSats flying in asynchronous orbits, so basically just different orbits so that they kind of intersect in different places at different times across the Arctic. Each of these CubeSats is no bigger than about the size of a cereal box. It's called a 6U CubeSat. They run on about 20 watts of power. I guess they weigh on the order of about 6 kilograms each. So they're very tiny little instruments, tiny little satellites. But what we've been able to do, and this is through a lot of technology development at Jet Propulsion Laboratory, is develop an instrument that is capable of measuring these far infrared fluxes out to 54 microns that only weighs 97 kilograms and uses an average of about 2 watts of power. So it fits well within the specs of each of these instruments. And by doing this, we're going to get 64 channels worth of information over this entire infrared spectrum. And we're going to use that information to infer both the surface emissivity, so how much radiation is really being emitted by the surface into the atmosphere, and also the Arctic atmospheric greenhouse effect, how much radiation is being trapped by clouds and water vapor in the Arctic atmosphere. The reason for flying 2 CubeSats is with 1 CubeSat we'll be able to map this out climatologically over all of the surfaces in the Arctic. With 2 and these intersections at different time lags, we'll actually be able to look at how processes like melting of the ice sheet or melting of sea ice or even snow landing on sea ice affects the emissivity. So if you have 1 CubeSat go over at 9 in the morning and the other at 7 at night, if something happened in between that, we can actually see how the emissivity changes and associate that change with changes in surface emissivity. So I've already talked about this a little bit, but these are examples of the data products we're hoping to get from PREFIRE. We're hoping to get profiles of water vapor vertically through the atmosphere. We're hoping to get spectral surface emissivity, so surface emissivity but resolved spectrally. Again, this governs exactly how much energy gets emitted from the surface to the atmosphere. And then thin ice cloud properties. We should be very sensitive actually to very thin ice clouds that are often very difficult to detect over bright surfaces. And then finally, with all this information, we're going to calculate those broadband fluxes I showed in that diagram at the beginning, which is the energy exchange between the surface and the atmosphere through emissivity and through the greenhouse effect. And then finally, we have a component of the project which I find really exciting, which is dedicated to making sure that these observations get used for the purpose that they were intended, and that is we have an ice sheet modeler on our team and a climate modeler on our team, and we're going to try to work with these groups to make sure that our new spectral surface emissivity models and our estimates of the greenhouse effect and cloud cover are directly incorporated into models or used for model validation. So here's my summary. Basically, the main point here is that there's a large uncertainties in these thermal energy fluxes at both poles, but I focused on the Arctic, especially for this group. They have significant implications for polar climate, especially when you account for the associated feedbacks using a full climate model. They also lead to uncertainty in surface processes. PREFIRE is offering a pathway to improving some of this knowledge. It's not going to solve the problem, but hopefully it will incrementally improve it. My question, and I think what I wanted to pose to this group a little bit in order to think about is, how we can actually interface best with things like polar modeling groups and other field project groups to make sure that the PREFIRE observations are kind of reach their maximum benefit to the community. So like I said, we do have some modelers on our team, but we would definitely like to engage the broader community that I think this group can actually help us reach out to make sure that our observations reach the widest range of people. So thank you.
Thank you, Tristan. I have a very similar question, I think, to launch the discussion, or a question that builds on your question. To start, maybe with the modeling thing, Sarah, perhaps the modelers on this team need to meet with the IARPIC modeling team specifically, as well as maybe some of the IASC modeling groups or something. I don't know if we can help facilitate those things.
Yeah, I agree. And I think people like, there's a number of people on the modeling collaboration team that will be, if they're not already engaged, are probably already engaged in these activities. So I think we can do some pretty good outreach through them as well.
Yeah, and tie this question into that. Does anybody else on the phone have questions, or I'll kind of build on Tristan's question here if not, but we can certainly stay on the line another few minutes. We try to keep the calls as close to an hour as possible, but I think that we can certainly facilitate a short discussion here. So does anybody want to ask a question?
I had two really quick questions. One is, and it's probably on your chart there, I just may have missed it. What's the swath width of your, and also what's the, one thing I worry about is CubeSats can be in a low orbit and then don't have necessarily a long lifetime. What is the projected time in orbit?
Yeah, so the swath itself, and I actually deleted the swath information in favor of the resolution when I was putting the slide together, because I wanted to add the mass and other things. So the footprint itself is it's going to be between 10 to 14 kilometers, which is about the size of a Ceres or an Ayres footprint.
Right.
With those. We are going to have 8 footprints across the track here, so that's kind of represented in this diagram, which gives us a swath of about 100, somewhere between 100 and 140 kilometers, depending on how things are configured. Your second point is a point well taken. The nominal mission lifetime is up here in the upper left. It's going to be 12 months. And that is because, as you say, we have no propulsion on the satellite. And so the satellite orbit will start to decay after about 18 months. And I think we can, this is obviously a bit of a conservative figure because we're trying to meet this requirement. But after about 2 years, the chances of us being in the same orbit that we started in is fairly slim. So the orbit will decay. It's a relatively inexpensive mission at this point. I think what we're hoping is that if we demonstrate that this technology, this little tiny instrument that takes up this little power and this little mass, if it works, we're looking at missions like ACCP and some of the other, that's the aerosol cloud convection process mission or precipitation mission. Some of the other missions that have been announced in the decadal survey, that those might end up deciding, well, we could use a little bit of a mid to far infrared instrument on our mission and can find space for us to fly on those missions for better continuity.
And I was just going to clarify, it's roughly 1 kilogram for the spectrometer.
Correct.
Yeah.
Hi, yeah, this is Brian Kahn. Sorry, I had 2 mute buttons. I couldn't introduce myself earlier. So I just wanted to follow up on Tristan's comment with the swath width, that we're not exactly sure how close the 8 pixels are going to be to each other. So there might be little gaps in between, and depending on what the final design is, it may be either 1 or 2 pixels worth of gap in between each pixel.
Yeah, so I guess that gives us a bigger swath, but then it would, obviously it would not give us continuity across the swath. So there's trades to be kind of thought about.
Yeah.
And what's the timing for the start of this mission?
Oh, that's a really good point too. So nominally about 2 years from now, or maybe a little more, we're looking at a spring 2022 launch, early spring. But the caveat to that, and the reason there's no information on these slides, is that as part of the EVI program, NASA does not require us to launch ourselves. Basically, they don't put the launch costs on the project. They find a launch for us. And so what that means is that we're not going to be a primary payload on any particular launch, and we're going to have to wait for an appropriate launch in our orbit, which is between 82 and 98 degrees. We're going to have to wait for an appropriate opportunity and then go with that launch. So we may be delayed up to a year or more even from that sort of nominal date. But the CubeSats themselves will be ready to launch by the end of 2021.
Tristan, this is Sandy. I apologize if I missed this piece. I see it just in the corner of the slide about this NRO MC3 ground station network.
Right.
So that looks like that's where you're doing your validation. What's the distribution on that network? Is it a single site or are there several stations?
There are several stations, and I don't have the information offhand about their distribution, but I think there's about 6 of them. I will say that right now is that's still a topic that's open for debate, since we haven't let's just say we haven't fully confirmed that this is going to be our network for downlinking data yet.
Okay, so that's for downlink. What about validation?
Validation will actually look a lot more like Seiji showed. One of the primary sources of validation we're going to use are the ground stations that Ceres already uses. That's for the surface observations. Actually, for the on-orbit measurements themselves, we're going to validate against some of these other sensors I mentioned that only go out to 15 microns. Those will still allow us to validate our measurements that go up to 15, because we actually do cover a lot of that spectrum as well. And then we're going to validate our integrated observations against the Ceres outgoing long-wave radiation measurement to kind of provide a benchmark there too. So we're going to use a lot of simultaneous overpasses with other satellites to do a lot of our validation. The other thing, although I'm glad you bring up the point, because when I mentioned coordinating with field projects, I think there's sort of 2 aspects to that coordination. One is that we would really like to be able to kind of expand the information provided by the ground observations to kind of a larger domain. But the other aspect of it, the reciprocal aspect of it, is we could really use some collaboration with some of the other field programs and other things that are being planned for the Arctic, where, for example, we might be able to put a prototype of our instrument on an aircraft or on a tower and make some measurements even before launch or especially after launch. So I would say that's something that we're looking for opportunities in it right now to do, and that's another reason that I wanted to kind of communicate with this group.
Yeah, it strikes me that the Barrow facility in the GMD is right now redesigning would be a great location for doing something like this, or I'm sure you've considered the DOE sites as well. And I'm a little rusty on some of this, but most surface purgeometers, they're only looking out at wavelengths in the 20 micron. Is that correct? So they'd get part of your gap, but not all of your gap.
I think they cover. I would have to dig deeper into that, but I think that they cover a larger range of wavelengths than that.
Okay, yeah. It's for some reason 3 to 20 seems like what sticks in my head, but they might go out further than that.
Yeah, and of course that does help, because like I said, we are making a spectrally resolved measurement. So even if we could validate half of our channels, let's say, and then do some other kind of an integrated validation against Ceres, that does provide us with maybe the 2 pieces we need to ensure that the measurements are validated across the whole spectrum. But yeah, to come back to your other point, the Barrow site is one of our top candidates right now for deploying some kind of an instrument to help validate our mission. We're actually considering using maybe a tethered balloon system, or developing a prototype that might actually work on a tethered balloon for doing that kind of purpose, because it would be nice actually for us to be able to get a little bit above the atmosphere and stare for a longer period of time. Aircraft would work as well, but then it's a shorter time of measurement, and it's a moving platform. So we're looking at both options as providing validation for us.
So I'll actually build on to Sandy's question too, and this is not my area of expertise, but both presentations are really interesting. So I'm asking, I think from an NSF program officer perspective, and so maybe Barry and Sandy can help me out with my question too. But what I think we have some other sites too besides, Barrow is certainly a good candidate. The DOE sites are good candidates. Thule has a lot of atmospheric observations where an instrument could be plopped. Summit has year-round technicians that can operate instruments, and we do have currently atmospheric observations. So I'm wondering for both of you, because Seiji talked about the different surface scenes and and what's needed. So if you had, if you could make requests of field types of experiments and things, you talked a little bit about putting instruments on towers, putting instruments on aircraft. What would you do, or how could we connect you with some of our core atmospheric groups so that maybe those measurements could commence at the same time or even before the mission starts? What are you looking for? What would be ideal?
So I think ideally what we would like to do, and I don't know if I ever had a list of my products. Well, if you take a look at this, you know, what we want to do is be able to couple. So like I said, we may be able to build a prototype. We're working on securing funding for doing that right now, or potentially using reserves for doing that. If we are able to build a prototype, then I think what we would need to do is have that coincident with these other measurements. So we you know, these are the products that we're going to be deriving from the observations, things like ice clouds, water vapor profiles through the atmosphere. So any site that does regular soundings or has maybe an ARRI or some other instrument that's capable of making high temporal resolution soundings would be ideal. And then we would like to have a site that obviously keeps track of what the surface is. Now, maybe in Summit, that's not that big a deal, although the surface emissivity can change a lot with snow grain size and spacing. So it would be good to have a site that has some observations, maybe visible observations of what the surface is doing and how the albedo is changing. It would be good to know when it snows and when there's a melt event. And so having these ancillary observations present, and that's why I think some of the sites you're listing are definitely sites that I'm aware of and that would be really useful. I think that's the key to making this a useful validation, is to be able to connect the physical parameters we're after to the spectral observations that we're going to be making and try to validate.
Yeah. Jennifer, does Summit have a LiDAR still?
We do, or we're, yes, I think so.
So that might give you those thin ice clouds or clouds, and the,
so
you still have ozone sondes and radioson launches, so that could give you the water vapor.
We have radioson launches. We don't do regular ozone sonde launches.
Okay.
That's not to say somebody couldn't do that as part of a project.
Yeah.
Or somebody couldn't help cover it. And then there is an upward-looking LiDAR at Thule as well. It's operated by the Italians, along with Jim Hannigan from NCAR, his instruments that I don't know.
Yeah, Jim's going to measure water vapor with his.
Okay.
His.
And so in the same building, there is an upward-looking LiDAR that they're usually they're just wintertime measurements. Kind of what I was thinking, and Barry, maybe we could follow up on this, and I think Sandy as well. Pulling together those groups of researchers with Tristan.
Yep.
So that Tristan could kind of even maybe just go through this presentation and those researchers can talk about their instruments, what they're capable of, or what they might have on the horizon for ideas.
Yeah.
And put together some observational.
So I saw that Summit got above freezing.
Yep.
Did it, was there any melt water at all, or it was not long enough for that?
It was above freezing for almost 4 or 5 hours. It's the longest melt event that we've had. So I haven't seen surface water measurements, you know, like but I believe so. I mean, I believe I know there was anecdotally water.
It would have modified the snow grains. So
right. Yes.
Yeah, and that's what we would like. And again, you know, if we had the ability to sit there and measure continuously for a while and actually looked at what the spectral emissivity looked like before, during, and after the event, and then use that to kind of test or develop algorithms, that would be extremely useful.
Yeah.
So Tristan, there is a list online of the instruments at Summit. I can confirm if it's updated or not. I know that Von Walden and Ryan Neely were just installing some new instruments looking at cloud vapor and other things. And so that is online, but I think I would put you in touch with them, as well as perhaps Connie Steffen, who gave the talk in June for us, and Jim Hannigan and Giovanni Mascari. I know you're already talking with Jim, which is great. And then I think that Sandy might have some ideas of folks as well. So maybe we should just do a follow-up discussion with some of the ground-based PIs to talk about what would be needed to really couple with these measurements for people. And I don't know, Seiji, you mentioned as well a need for additional validation sites and things. Is that something? Does that sound like that would be going in the direction to help some of the variability that you identified?
Yeah, we are interested in all types of surface measurements, and as a series we have a cloud retrieval groups, and so all the measurements that Tristan is interested in, and we are interested in as well.
Seiji, you had a site in Greenland. I wasn't sure if that was Summit or...
It was Summit.
Okay. Good.
Yeah, that was Summit. Yeah, and I think that's the quality of Summit observation is very great, and we have some other radiation measurement over Greenland, but the quality wasn't as good as that Summit observation. So we really appreciate whoever maintained the observation, and that was great. That is great.
That's great, but and also a lot of those. Well, Barry and I both sponsor observations at Summit, and so for us, I think it's important to connect you guys with the researchers, because their research projects are, just a few years, and then they put in new proposals and they renew their objectives and hypotheses and things, and so tying it to something like this for people that are starting to write proposals would be really helpful for them. Barry, I don't know if you want to build on that.
No, I agree, and. And NASA, I think there's some advantages for NASA to, Summit's kind of a unique place because it's also at high altitude, and so there's some, comparing that to some low altitude Arctic sites, there's a lot of value there for us.
Yes, and Thule, well, similar to Barrow, I think it's a little further north, but it's a very easy place to operate and make things happen. We have a building there dedicated to atmospheric observations. We just need people and instruments and people to be successful with proposals. So it's a platform, a location that's available as well. So, but Summit is the unique place for validations. So we can follow up.
Steve,
yeah, go ahead.
Can I?
Yeah.
Steve Peckham in the Cold Regions Lab. I just wanted to toss out another potential site. We are collaborating with University of Alaska Fairbanks. We have a facility up there. We have towers. We do a lot of meteorological observations. Just going to toss it out there as a possibility of another place to, if you want to test out an instrument and have a lot of these observations, be glad to talk about it.
Great. Maybe we'll put you on the hook for a presentation at some point.
Don't threaten me like that.
You can tell us about it. No, that's good to know. And that's kind of information we're all looking for. Okay, well, I think we've kind of kept everybody quite a ways past the time, but it's a good discussion. So maybe, Sarah, I don't know what the next step is, but we can talk, or Barry, we can talk in our co-lead meeting and follow up to get everybody, connect all these people so that
we can have a future meeting to try and close the loop on some of these opportunities.
I think that would be good.
Can I ask a slightly related question, which might also be a bit of an extension of what you were just saying? So you mentioned earlier that there is this modeling group as well, or modeling collaboration. I'm wondering if, in conjunction with having this meeting between just the observation groups, the field site people and the satellite observation people, it might be good to get maybe to even frame some of these measurements or these ideas around some kind of a modeling component as well. Like, is it possible to invite some of the modeling people to join the meeting?
Absolutely.
Yeah, we have joint meetings all the time. So
yeah, I think reaching out to Richard Colither may make the most sense to start with, and then connect through him.
Okay.
Yeah.
Yes. Yes. The answer to the question is absolutely, we can do that. And I think, not just looking for projects to fund and the next things coming down the pipeline for science, but for us, when we interact with lawmakers and agency heads and things, the thing that's always brought up in conversations surrounding climate change is model uncertainty. So this is a really relevant thing to pursue and bring all these people together. So anything we can do to facilitate that, I think, is certainly of interest to us.
And Tristan, perhaps one of your modeling PIs can give the presentation to the modeling group.
Absolutely. Yeah, that would be great.
Okay, we'll make some plans. Any other last questions or comments? There was one chat in here, Sarah, I don't know. Oh, Sandy signed off, okay.
Yep.
Okay. Any announcements or anything? We have our next meeting. Let's see, I think Tristan has to stop sharing. We can go back to the agenda. Okay, so our next meeting will be on the merged observatory data files. And I guess we haven't determined a date on that. Is that a joint meeting? I think it's
I believe it's a joint meeting with the data group.
That's right. Okay.
Yeah.
Okay. So that's our.
You can throw in we use the site as a platform to announce. So if you haven't joined IARPA collaborations and you just got here by word of mouth, join because you can put comments in here to follow up with any questions for Tristan or Seiji or Jen and Barry to keep the conversation going. And this is how they'll announce if there's going to be a follow-up meeting with modeling and with ground-based surface observation PIs.
Yeah, that was great. And so, yeah, there will be more to follow on this, everyone. So I think following the announcements to see when the next meetings are, and then we'll follow up by email, certainly with Tristan and Seiji, to try to pull some of this together. So we really appreciate it. I want to thank both of our speakers today for this really great presentations and great conversation.
Thanks, everyone.
Thank you.
Great, thank you.
Okay, we'll be talking soon.
Okay.
Right.
All right.
Bye.
Bye-bye.
Bye-bye.